everyone. Today we're looking at Newton's law of universal gravitation. So we've looked already at Newton 1, Newton 2 and Newton 3. So what is Newton's law of universal gravitation? It's amazing. What it states is that between every object in the universe there's an attraction force working. That means there's an attractive force working on me, onto my camera, or between me and Mars. Alright? So if we look at this, it states that between any two objects or bodies in the universe, there is a force. And that force is directly proportional to the product of their mass and indirectly proportional to the distance d, or we can also use r for radius, between the centers of those two bodies. So in effect it is F for force equals, now we're going to bring in a gravitational constant here to put the equal there, and then we're going to say, okay, the mass of object 1, mass of object 2, and divided by the square of r. So that is Newton's universal gravitational law. So you can see, if I look at this, that the bigger the mass, the bigger the force. So the mass between, let's say, me and Earth, there's a force, which we know it's gravitational force, yes. We also know that we can talk about gravitational force, and I can also talk about that as your weight. So there's also, we can say Fg, which is your gravitational force working onto an object on the surface of Earth, which equalizes then your mass times gravitational acceleration. And we call that one weight. But it's the same thing, it's two objects. It's me standing on the Earth and it is Earth. So it's two objects, there's a gravitational force working between the two of us. All right. Now I want to bring in here already Newton's third law that states, can you remember? When one object exerts a force onto another object, then that object will have the same force, equal magnitude force, but in the opposite direction of that force. So when I say the Earth is attracting me with a certain force, which is my weight, so Earth on me, that means that me also attracts Earth with the same magnitude. Newton's third law. All right, so don't let them fool you there in a short question or a multiple question kind of scenery. All right, so if we look at this equation, we see that firstly, it has to act on the centers, between the centers. So don't let them fool you and they give you only the distance between the two objects. And I immediately want to just point out to you, what is the unit that we measure distance or radius in science? What is the standard unit? And you know what, it's one of those moments that you sit there in a question paper and it suddenly hits you and you're like, oh my goodness, is it meters? Is it kilometers? What is it? Especially when it is planets. Let's say it is Earth and it's Moon, or it's Earth and it is Mars. And now they give that distance in kilometers. And then I start to think, yeah, well, that makes actually sense, because it's a long distance. No, be careful. That unit for radius or distance must be in meters. All right? We know that our mass in physics is always in kilogram. It's only in chemistry that it is gram chemistry. But in physics, remember that it has to be kilograms. And we now know, of course, that my Newton, that force measures in Newton. So one thing that I could ask you, for instance, if we want to start playing around with units, I could tell you, all right, use this law, this formula, and work out for me what would be the unit of G. What would be the unit of G, the gravitational constant? So what I'm going to do, I'm going to try and get G on its own. So I'm going to take away radius square. I'm going to multiply it on this side. So what do I have on this side? A Newton. So then it is Newton times a meter is meter squared equals G, and it's kilograms times kilograms, so that is kilograms squared. So how do I get rid of that? That's going to come to this side. Let me just turn it around. So it's Newton meter squared divided by kilograms squared. And what do I do with that? I can say times kilogram minus 2. And there I have then shown where is the unit of G coming from. Okay, just keep those things in mind, because that's always what I try and ask you in different ways. All right, so let's get back to this formula. So in which direction will this formula work? Because force is a vector. So in which direction will that force be? Always attraction towards each other, always the direction. Okay, so what we're going to then do is they're going to now, of course, give you, let's say you've got the sun and you've got the moon, the distance between them, this is the mass of the earth, mass of the moon. Work out what is the gravitational force between the moon and earth. Easy peasy, use your formula and substitute, and then just get to your final answer. But of course there's always going to be a catch. So let's have a look at what kind of ways they can kind of confuse you. All right, now one of them is, for instance, where they say an object is on the surface of the earth. Okay, so it's there. Okay, now let's say we move that object to a distance 3 times the radius of earth. So 1 radius, 2 radius, 3 times the radius of earth. So it's 1, 2, 3. So there is the object now. Let's say it's a satellite or whatever. Okay? So the moment they say that, and you're now going to substitute R as 3R. What did I do wrong? What did I miss? Is it 3R? No. Why not? Because I missed that it has to come from the center of the object, in this case Earth. So I have to have already the radius of Earth and then 3 times the radius of Earth above the surface. And that becomes then 4 times the radius. Okay, so just be careful. Another way, like how they always also like to ask you this formula, is of course by not giving you any magnitudes, by just working with ratios. For instance, they say, and it's again in a multiple type question, they will say the force between 2 objects, mass 1, mass 2, with a distance r between each other equals F. What will the new F be if the mass of the one doubles, the mass of the other one times 3, and the radius or the distance between them halves? Okay, so how are you going to now get it? What is F now going to be? You know what you do? You would do it like this. The moment they start, so let's say G will always stay the same, it's a constant. So now they're going to say, okay, what will be the new F, the new value of F? Let's say the one of the object, the mass doubles. So it's 2 times that mass. Put it in. The other mass, let's say, becomes, stays the same. Okay, so that one stays the same. And the radius between the two objects, half. So I'm going to put in here a half r. Remember, put that in brackets and your square. Never forget your square. Never forget your square. That's where you're going to lose your marks. Okay? So what are we going to do now? Now what I would do is then bring all those new different values, bring them to the front. That is 2 times g m n. It's the same thing if I say 2 times g or g times 2. It's the same thing. Divided by, and I do the same here, but now be careful, I've got a half square. So what is half square? That will become 1 over 4 r squared. Okay? Now look at this. Isn't this looking familiar? Yes, that was f. F equals gmm over r squared. So in that, I can then say that is f, what f was, what it used to be. And then I'm just going to say, okay, what is 2 divided by a quarter? So what is 2 divided by a quarter? That will become 8, because it's 2 over 1 times 4 over 1, so that becomes then 8f. So the force becomes 8 times bigger. Alright, so that is how you're going to do this. You want to do another one quickly? Are you going to be okay? Alright, otherwise just rewind the video quickly and have a look again. So just put your new values in, bring them to the front, and then you say, okay, that is what f was. How is the change going to now happen? And then just get that value. Very often they leave it as a ratio. It could be f over 8, for instance, on the A, B, or C, D answers. Okay. Alright, so let's continue. Remember we talked in the beginning, I also pointed out to you that weight is also an attraction force between you and the earth. So while I'm talking about that, let's quickly recap. What's the difference between mass and weight? Mass in kilogram only measures your material that you're made of, all right? That is mass. It's a scalar, no direction. But what is weight? Weight is a force, and it is a vector, and it always has a direction. So your mass can't change. If I stand on Earth, my mass is, no, I won't say, 60 kilogram. I hope. Anyway, so on Earth, my mass is 60k. What is my mass on the Moon? Also 60 kilograms. On Venus or on Mars, also 60 kilograms. It's not changing, okay? But what is weight? And now we're going to have to look at G. Because G is my gravitational force where? On Earth. And we talk about G as a constant. We say G is 9.8 meters per second square on Earth as a constant. But I'm going to now show to you it's not a constant. Not really. Okay, let's have a look. So I want to show you now something. If this is the force between me and Earth, so let's say the one is me, let's make it a small m, and the other one is Earth. And this is the distance between the center of the Earth to the center of me, okay? That is the same thing, because then this would only be, I would only work out my weight. And do that, just for fun, do that. Use your gravitational constant, 6.67 times 10 to the minus 11, okay? Use that value, use your mass, use the mass of the Earth, and oh yeah, by the way, it's always standing on your what? On your sheet, your data sheet, that you do get extra. The radius of the Earth is also on there, okay? So use that values and the radius of the Earth, and then work out what is the force between you and the Earth in newtons. And then do the same thing. Use your mass and just say times 9,8. You know what? You're going to get exactly the same answer, because it's the same thing. Your weight is just the attractive force between you and the Earth. And this formula is also working out the force between any two objects, in this case you and the Earth. So if that is true, then I can say that these two, now I can use it like this. I can say, okay, then if this equals F and this also equals F, then that equals this. So let's do that. And what do we see now? What we now see is that my mass, look at that, falls away. So my mass does not really matter when I work out G. So if I ask you to work out the value of a gravitational acceleration, let's say on Mars, can you see what? Now you've got a new formula. Coming from there, now we've got a formula stating that gravitational acceleration equals G, the same constant, times the mass of the planet that you are standing on, divided by the radius square of the planet you're standing on. So it's got nothing to do with my mass. Wow, wait a minute. Let's think about that. Galileo actually did an experiment somewhere in the 14th century where he took two objects onto the Tower of Pisa and he dropped them. And he wanted to see if they would fall and hit the ground at the same time. Would they accelerate towards Earth with the same acceleration? If there is no air resistance. So if there is no air resistance, and I would draw a little graph here, let's say it is a force diagram, a force graph. So that's my F air, which would be my air resistance, and that would be my gravitational force, Fg or W for weight, but there is nothing here. There's only the pull of the Earth onto that object. Would they fall with the same acceleration? A huge mass and a very small mass, are they going to hit the ground at the same time? Yes, they do. It's a very interesting experiment. Professor Brian Knox on YouTube has got a stunning video where it's a classic one where you have a heavy object out of metal and you have a feather, and when they pull or suck all of the air out of that room, that you have only a vacuum, and you would then drop them, okay, the ball and feather experiment, then they will fall and hit the ground at exactly the same time. That feather drops like lead. Douche. You wouldn't believe it. And it was already proven by Galileo. And if they ask you to prove that mathematically, then in physics what you're going to do is you're going to do this. You're going to say, okay, that is the equation for Newton's gravitational force. That is my equation for weight. It's actually the same thing. And so I'm going to just equal them to each other. I can see my mass is going to fall away, and I'm only left with G equals what? So I can work out G, that over square R. And the moment I say this, you have to now query me and say, ma'am, that means that acceleration is actually dependent on how far above the surface of that planet you are. Because it's an indirect, look at this. So whenever R becomes bigger, then G is going to become smaller. Whenever R becomes smaller, then G is going to become bigger. Or the other way around, R gets bigger, then G is going to be smaller. Okay, what does it mean? It means G is not a constant. It means that the further I move away from Earth, the higher I go, the higher I go, the higher I go, R becomes bigger. So what is G going to become? Lower. A lower value. So if that is true, if G is become less the further I go away from Earth, it means, girls, that's a way to lose weight. I can weigh less if I just have to be far away from the center of Earth. Because then G becomes lower. Why is G's value going to go down? G's value is going to go down because R is going to go up. And they're indirectly proportional to each other. You see where I'm going? So, actually, G is not a constant. So why do we say that? Why do we give it as a constant in your papers and on your data sheet? Because in a distance for about 10 kilometers above Earth's surface, it's not really going to matter much. You're still going to get about 9,8. It's only the decimals that's going to change a little bit. So yeah, of course, it has to go to extreme values for it to really affect G. But it's true. You could go so far away from Earth that G becomes 0. But of course, then you shouldn't be then around anything else again, because then there would be a G towards that planet. All right, so it's a very interesting subject. Now we can go on forever about this. All right, so now we're going to have to look at how are we going to work out typical questions regarding Newton's universal gravitational law, which states that each body in the universe attracts each other body with a force, and that force equals the product of the two masses, and it's indirectly proportional to the distance, or R, between the two objects' centers. Very important. So never forget, if that is your object, that you have to measure from the center of that object because of its mass center, which sits in the center of that object. All right, so let's have a look at an example. Okay, so this video is only going to be the theory. I hope it helps you. The next video, I'm going to look at an example of a question for about 5 or 6 or 7 marks. Okay, but believe in yourself, you can do this.